On to the calculations. So we will start out with a pair of converging lenses that are 45 centimeters apart, different focal lengths, object over on the left, blah blah blah. I would suggest drawing a little diagram to keep track of where everything is. So let's get a couple of lenses here. We are given that this is 45 centimeters. Everything's in centimeters, so we don't need to worry about converting anything. We're not dealing with diopters, so we don't need to worry about meters. Okay, this guy has a focal length of 10. This guy's got a focal length of 8. I'll call this A here, B here. And then we've got an object, 22 centimeters over here. So 22 from there to there. And we want to find the final location and magnification of the image. I think I forgot to mention the magnification just gets multiplied for the two lenses. So our general equation for magnification in terms of distances is dido. Here we're going to keep track of which lens we're talking about. So DIA over DOA. And then we just multiply that by another negative dido, DIB and DOB. And obviously you can get rid of the negatives since you have two of them, so it's just the object distance and image distances plugged into this guy here. We'll give you the total magnification for the final image with respect to the initial object. Alright, so let's get at it. We're going to plug into our lens equation 1 over DO, which is 22, plus 1 over DI, and I'm going to specify DIA here because I'm looking at where the image is from this first lens, and I don't even care about that second lens yet. It doesn't affect the properties of this first lens and the light going through that first lens. Okay, we set that equal to the inverse of the focal length, and we've got this here. We're going to solve this for DIA. I'm going to skip a little bit of the algebra because you've got it down by now, right? And you get 18.3 repeating centimeters. So that is a little ways this way. It's going to be inverted. Doesn't really matter, but that distance there, 18.3 centimeters to our image. Now I need to convert this location to a distance with respect to lens B, because this is DIA, but it's also DOB. The image from the first one becomes the object for the second. So I just have to take 45 minus 18.3, repeating, and that's going to give me the object distance from B, and that works out to be 26 and 2/3, 26.6 repeating is this distance here. And then I can plug into the same lens equation, but now dealing with lens B. So I've got 1 over 26.6 plus 1 over the image distance from lens B equals 1 over the focal length of lens B. Do a bit of algebra, and I get the location of the final image is 11.4 centimeters from lens B. This did come out to be positive, which means that my image is over here somewhere, 11 centimeters from this guy. And sometimes the questions might ask you it might ask you specifically how far is the final image from the first lens. So in that case, your calculation is always going to give you the distance from the second lens, and then you're going to have to use this separation distance here to adjust it back. So you just have to add 45 and 11.4, and you could report it either way. Alright, if we want to find the magnification now, we have to plug in these numbers here, those two that we calculated, as well as this number here and this number here, right? So image distance of A, that was our 18.3. Don't put in rounded answers here, by the way. Object distance was 22, multiplied by image distance of B, which was 11.4. There was more digits than that, but anyway. And object distance was the 26.6 repeating. So you want to grab all these values out of your calculator so that they are not rounded. Yeah, this was 42857 or something like that. Okay, you multiply all that stuff through and you get 0.357 is the magnification. So that tells us that our image is smaller than our original object. This also comes out positive, which tells us that it's upright, which we expected because these converging lenses, when they're making real images, they flip the image each time, and if it got flipped twice, it's going to end up upright. Okay, next problem is identical to this one, but now we have our lenses scooted closer together. So now they're only 10 centimeters apart. And you probably have guessed why we did that. But let me go ahead and diagram the situation again. So this guy has a focal length of 10. This is now a distance of 10 instead of 45. This guy still has a focal length of 8, and we still have our initial object over here at 22 centimeters. Now, moving lens B, lens A, lens B, closer, again, doesn't affect what goes on with lens A, so we don't even have to do our calculation again. We know already that the image distance from lens A was 18 1/3. Now, this is only 10 centimeters, so that puts it over here somewhere, is going to be the image from our lens A. So this is DIA/DOB. And from lens B, if this total length here, from A to the image is 18.3, but we've got this 10 here, so this distance here is just going to be 8.3 relative to lens B, so that's what we're going to plug in to our equation for lens B. So 1 over 8.3 repeating plus 1 over the image of lens B distance equals 1 over that focal length, and now we find an image distance of 4.08 centimeters. So that image ends up being a bit closer over here. We'll say right about there. Okay, still a real image, got flipped twice, even though we intercepted those rays before they actually went through. We still consider this a real image at the end here, and we have it flipped twice. If we want to find the magnification, we plug in the same 18.3 and 22 that we did for lens A. And now we have different lengths for lens B. So we've got 4.0816 over 8.3 repeating. Multiply that through. You get 0.408, so a little bit larger than last time. The magnification is a little bigger. Also positive, so we end up with an upright image still. So having this, oh wait, I screwed up. And that was the whole point of doing this second example. Sorry, you guys need to stop me, I tell you. Because the image is on the other side of lens B, we actually need a negative sign on this guy here. So this is new. That only happens when we have combinations of lenses. Do we have a negative object distance? So DOB was negative 8.3. Now the rest of these calculations are actually accurate. When I plugged these in my calculators, I had the negative. I just forgot to write it here when I was transferring it. Okay, so yeah, that's the new thing. Pay attention to that. Be careful with your signs, otherwise you won't get the right answers. Alright, let's do one problem with Lensmaker's equation. If you remember that one, it was 1 over the focal length equals the index of refraction of the material that the lens is made of, minus 1 times the quantity of 1 over R1 plus 1 over R2, where these R's are the radii of curvature of the two surfaces of the lens. So double convex lens, which is kind of the example of the day, I guess, we have two different radii of curvature, we have a focal length, we want to find index of refraction, so we're just going to be plugging into this guy. Now, if it said a double double concave lens, sometimes it might just tell you that these are the radii, but you're going to have to know if it's concave that you will need negative signs on there. This one's convex, so we don't need the negative signs, but they do have negative radii of curvature and negative focal lengths if we have concave surfaces. Alright, so let's get to it. We've got our focal length, so 1 over 33.6 equals n minus 1, n is what we're going to solve for, times 1 over 28 plus 1 over 74. So you do a bit of algebra, you can go ahead and divide this, and throw that in your calculator, divide it across. Anyway, you'll end up with n minus 1 equals 0.604575516, blah, blah, blah. Move the 1 to the other side, and you get n equals 1 point all that stuff, or if we round it to 3 sig figs, 1.60. No units on our index of refraction. So this one's pretty straightforward. A little bit of algebra, but nothing too confusing there. Okay, see you next time.